Bye, everybody. Ready when you are, Steve.
All right, this is Scott here, Scott Abbvie, filling in for Carl today. Carl's out, so I'm here to take over to introduce today's agenda. Thanks to Steve and Rio and everybody at the CCHF for setting this up. And our speakers today, Alison Wendlandt from Massachusetts Institute of Technology. I will be speaking on selective catalytic transformations of carbohydrates. And Eric Voight from Abbvie, who will be talking about beyond the rule of five synthesis of antiviral drugs at Abbvie. Appreciate everybody who's joined in today, and looking forward to this alumni session from the University of Wisconsin. So let's take a look at the next slide, please. All right, and just looking at the upcoming virtual symposium on September 15th for the CCHF, we have a session with Ken Hauk and Masayuki Wasa from Boston College, and for the ACS DOC, we have the Academic Young Investigator Symposium on August 7th, the Power of Women in Organic Chemistry from the 13th to the 14th and the virtual meeting for the ACS San Francisco. Steve will be talking a little bit about that in the next few slides. And in October, we'll resume our normally scheduled virtual symposium with Nuno and Neil on the 21st. So I'm going to pass it over to Steve to talk about some of the upcoming sessions.
All right, thanks a lot, Scott, and thanks for filling in for Carl. Unfortunately, Carl was the funny one, so this probably won't be as entertaining as these typically are. But I'm going to talk a little bit about some of the upcoming DOC and CCHF virtual events. We have a pretty nice schedule over the next month and a half. So, please feel free to tune in. The first is the Academic Young Investigator Symposium on Friday, August 7th. These are young faculty members who are around the point where they're up for tenure. This normally would occur as part of the ACS virtual meeting, and these talks will be available as on-demand talks at the virtual meeting. But we've decided in partnership with CCHF to do this event completely live on August 7th, a little bit before the actual ACS meeting. It'll consist of 20-minute talks for most of the day, and followed by Q&A. So, please feel free to join in. We'd like to have a big audience for that. After that, the next event that's coming up, Ria, jump to the next slide, is the second annual Empowering Women in Organic Chemistry Conference. And this has a really nice lineup of speakers that are shown on this slide. It's a two-day virtual event. Having attended this personally or in person last year, it was a really just phenomenal experience, both in terms of the science as well as my personal experience attending this conference. I would highly recommend that anybody registers. It's just going to be a really phenomenal event. They already have hundreds of people who have registered, so I would suggest registering now to reserve your spot. And then, Ria, if you can move on to the next slide. And I'll talk a little bit about the ACS Fall 2020 virtual meeting. So I think everybody is aware that the meeting has become entirely virtual. There won't be any live components in San Francisco. It's going to occur from Monday through Thursday, August 17th through 20th. And the schedule is shown on this slide. Basically hasn't changed since last month when we talked about it being tentative. Basically, there will be opening events, plenary lectures, things like that from 8 to 9 in the morning Pacific time. These are live and all ACS events. And then from 9 to 10, there will be live posters. Posters will be on demand the entire meeting, but there will be, during these times, there will be Zoom rooms for people to network. From 10 to 12, there will be semi-live broadcast technical programming, 1 track per division. 12 to 1, the second poster session, 1 to 3 additional broadcast programming. So just a quick note on that, on the meeting itself. There will be 2 types of talks: the broadcast semi-live talks, which consists of a recorded talk at a specific time, followed by live Q&A. And then there will be on-demand talks, which will be available for the entire meeting. So, Rio, if you could switch to the next slide. The Division of Organic Chemistry's broadcast events are shown here. Monday, we are actually going to have our annual Tetrahedron Award Symposium, this year in honor of Professor Peter Schultz. In addition to Pete, the speakers will consist of Professors David Liu, Alana Shepherds, and Kevin Shokat. That will be an all-day event as far as our live programming. After that, Tuesday, Wednesday, and Thursday, we will resume our standard tracks, the symposia that typically you see at ACS, 20 to 30-minute talks. So Tuesday and Wednesday are mostly synthetic focused with the typical new reactions and methods, CH activation, asymmetric reaction syntheses, photoredox chemistry, as well as the live Sci-Mix poster session, total synthesis of complex molecules, heterocyclics and aromatics, green methods, and biocatalysis, protein, peptides and proteins. And then Thursday will consist of flow chemistry, molecular recognition, physical organic chemistry. So, you know, we hope to have a fairly nice event, and I think that this is going to be a really nice. I think this is going to be a really nice meeting. So we hope you all attend. Transition over to Scott, who's going to talk a little bit about ACS awards.
Yeah, thanks, Steve. So we'll get into the season where we're going to be announcing the winners of the 2021 ACS National Award recipients. Some of the ones that are generally concentrated in the DOC will be the ACS Award for Creative Work in Synthetic Organic Chemistry, the ACS Award Pure Chemistry, the Corey Award for Outstanding Original Contribution, the Gunther Award for Natural Products, the Cope Awards, Cope Scholar Awards, the Norris Award for Physical Organic Chemistry, and the Herbert C. Brown Award for Creative Research in Synthetic Methods. And there's a lot of other ones, but those are the ones that are most highly tied to the DOC specifically. Please, for more information, go to the website shown there below, as we're also looking for nominations for the 2022 awards that will be announced next August. Those nominations will be close on the 1st of November this year. While it seems like 2022 is quite a ways away, and at the rate this year is going, it may seem like a decade. But yeah, we're looking for some nominations for the 1st of November 2020 for next year's awards. In addition, there are a number of other awards, such as the Technical Achievement Awards, the Young Investigators for next year awards. And so there's more information on those at the DOC website. So please have a look at that, and those nominations will be soliciting nominations throughout the winter and or early winter and late fall for those. So please nominate your colleagues for those awards. Thank you. Rio, if you could, the next slide. Thank you very much. And so the first set of awardees that we have, are the set of awardees that we have to honor today, actually is the SURF fellowships that were given out this year. We have 16 winners that are all on this slide. We thank Michelle Trendubé, who's part of the DOC Executive Committee, who's been supporting this for years now, and she put this all together and got all the nominees and the awards out. So congratulations to all the folks that have shown here that are the SURF awardees for this year. That's a $5,000 award based on the merits of their research proposals, their academic records, and the faculty recommendations. These are for undergraduates to carry out summer research before their senior year. And we'll be looking for next year's nominations again later in the fourth quarter of 2020. And really appreciate all the sponsors, and looking for some great congratulations to those folks and super nominees for next year. And we're planning on discussing next time, I think, some of the winners this year for the Young Investigators Industry and Technical Achievement Awards, and other award. We'll be recognizing other awardees as this symposium series goes along throughout the fall. So really well done, everybody. Thank you for the DOC and support from all these companies for these awards. And I think we're just about ready to start with Alison. Steve, you're going to take it away? Oh, sorry, one more.
Oh, and feel free to tweet us with any comments. But with that, let's get started. So for our first talk of the day, everybody will join me in welcoming Professor Alison Wendlandt from MIT. Alison began her chemical education at the University of Chicago, where she worked with Professor Sergei Kozman, and then moved to the University of Wisconsin-Madison, earning her PhD with Professor Shannon Stahl. Very productive, with 6 first author publications, developing a number of catalysts for aerobic oxidation chemistry, largely focused on copper and ruthenium. And for all of this work, she was a 2016 Reaxis Prize finalist. Alison then moved to Harvard as an NIH postdoc, working with Professor Eric Jacobson on the formation of quaternary stereocenters using chiral H-bond donor catalysis. In 2018, Alison began her independent career at MIT, where she already has a fairly large group, and from your website, I'm not really sure, but it seems to include some sort of a dinosaur. Maybe you could explain that to us. Earlier this year, published her first paper in Nature on the synthesis of hard-to-come-by sugars through site-selective epimerization reaction, which she'll talk about today. So welcome, Alison, and looking forward to hearing your talk.
Great. Thanks so much, Steve, for a really nice, kind introduction. Let me just get shared here. Move all this stuff. I have to say, I don't know what you're talking about with the dinosaur. My group runs the website, so I'll have to talk to them about that later. Sorry, hide. Okay. Laser pointer. Okay, so some of you may be at this moment thinking, oh no, I came to a carbohydrate talk. I'm afraid you did. But let me try and reassure you that my group is a small molecule catalysis group, and that our interest, at least my interest, in carbohydrates is really, first of all, the challenges presented by these molecules in terms of regio-selective, diastereoselective, product-selective manipulations, but also the opportunities that they present to impact adjacent spaces. So for example, glycobiology or drug discovery, drug development, as well as biomass conversion. So either on a molecular scale or a macromolecular scale. So I guess I have to admit I was somewhat surprised to learn that there actually aren't so many monosaccharides that are actually biomass available, so abundant on sort of commercial scale from biomass sources. Though of course we think of these as sort of broadly accessible chiral pool materials. So really it's just these 5, right? So glucose, xylose, mannose, arabinose, galactose, that can be obtained directly from the simple storage and structural biopolymers like cellulose, hemicellulose, starches, and so on. So this is in stark contrast to the remarkable diversity of so-called rare monosaccharides. These are typically microbially generated monosaccharides, which differ from the canonical mammalian monosaccharides in, for example, their relative or absolute stereochemistry, the presence of carbon-carbon bonds branching in the carbon backbone, deoxygenation or over-oxygenation, as well as unusual substitution patterns or element substitutions. So a remarkable diversity in the kinds of monosaccharides that are generated in nature. And of course, this pales in potential comparison to the kinds of molecules that may be made by humans, right, where we might approximately reach sort of infinite possibilities in terms of the kinds of sugars or glycomimetic kinds of compounds that could be generated. But it's exactly these sort of rare monosaccharides that play such an important role in the selectivity and potency of many the bioactive natural products that we know and love so well. And I just, if you'll indulge me, I want to give sort of two kind of detailed examples of how, though we may think of this as the sort of, the aglycone as the sort of natural product, that sugars can really play a powerful role in, like I said, selectivity, potency of these molecules. So first example is probably familiar to many, if not most of you, is the example of vancomycin. So of course, this is a sort of drug of last resort for the treatment of certain gram-positive bacterial infections. And its mechanism of action is that it inhibits the transpeptidation step in the peptidoglycan biosynthesis or maturation of the peptidoglycan. And it does so through binding the D-alanine motif of this sort of terminal peptide, sort of as I'm kind of trying to draw here. And equally remarkably, the antibiotic resistance arises from the mutation of D-alanine to D-lactate. So the single point mutation of N to O disrupts the stabilizing hydrogen bonding interaction as well as introduces a destabilizing electrostatic repulsion that results in something like 1,000-fold less binding affinity of vancomycin for its target. And so it is, I think, remarkable then that it was actually through modification of the sugar moiety, so far away from sort of the business end of sort of substrate binding, that resulted in the development of vancomycin derivatives that recovered activity against these resistant strains, but also retained activity against the sensitive strains. And equally remarkably, it was through a novel mechanism of action that is the inhibition of a transglycosylation step rather than a transpeptidation step in the maturation of the peptidoglycan that resulted from these substitutions. A second example I'll give is that of doxorubicin. So this is a representative example of the anthracycline family of drugs that has sort of two faces of this molecule. One is the sort of anthraquinone portion, which is responsible for DNA intercalation, inhibition of DNA polymerization, as well as this sort of eastern portion of the molecule, including this sugar residue that's responsible for binding to the minor groove of DNA. And so I think remarkable effects of changing the sugar that can completely destroy the cytotoxicity of these molecules. So for example, changing from the beta anomer to the alpha anomer, or removing the sugar entirely, again, results in no measurable cytotoxicity. But conversely, of course, strategic modification of the sugar residue has led to the development of second generation, even third generation variants of the doxorubicin substructure. So variants that have maybe enhanced potency and reduced off-target toxicity. So here's the basic idea of what we sought out to do, which was take these biomass-derived monosaccharides, which we have ample access to, and to develop key enabling catalytic selective transformations to open up access to these bioactive, important, rare monosaccharide substructures. So in a sense, kind of a target-oriented methodology sort of a project. And the objective, of course, as I've sort of laid out, is that access to these kinds of rare monosaccharides, either natural or unnatural, could facilitate the diversification of important glycosylated or sugar-based natural products or drugs, as well as facilitate the development of important man-made sugar-based molecules. So we're interested in sort of accessing all of these different I guess, families of rare sugars. I'll only have time to talk about the work that we've done on epimerization. And I think let me apologize, in a talk of this sort of length, I won't be able to sort of do justice all of the important work that's been done on accessing these kinds of molecules. So I'll just give you kind of a light overview on how they're sort of typically made. So it turns out that one of the best ways of accessing rare sugar isomers is through isomerization reactions. And so this is one of the oldest named reactions. You can take glucose, you can treat it with a sodium hydroxide solution, and you can actually access all of the sugar epimers all at the same time. And so these reactions proceed through aldose-ketose isomerization pathways, so via these enolization mechanisms that are essentially completely racemizing. And so under basic conditions, you basically, there's no problem in terms of reactivity, but of course, selectivity is a sort of paramount challenge. The sort of two very sort of sweeping approaches to selectivity, and again, I'm apologize for sort of generalizing here, are first through the use of protecting groups. And so I'll give you a representative example of the epimerization of glucose to allose is achieved through the use of protecting group based selectivity. So starting from protected furanose form of glucose, leaving group activation, deprotection, reprotection is the pyranose form, bimolecular substitution with inversion of stereochemistry at C3, and then deprotection affords allose. So I think the sort of obvious aspects of sort of step and atom economy aside, I think one of the real problems of using protecting group strategies to achieve selective reaction outcomes in carbohydrate chemistry is actually that they, for each product, there can be a bespoke protecting group scheme or solution. So for example, C3 epimerization of glucose will require a different protecting group scheme from a C4 epimerization of glucose. And similarly, C3 epimerization of glucose versus galactose will also potentially require a completely different protecting group scheme. And this is part of what has made, what has led to the requirement for some somewhat specialized knowledge in the area of carbohydrate chemistry is just the need to sort of know all of these sort of different tricks in terms of protecting group installation and removal. A second, I think, really important strategy for getting selective epimerization reactions to work is the use of biocatalysis. And so here I show you just one example of the so-called isomer enzymatic isomerization scheme. This is basically a strategy for stitching together different enzymes such that any hexose or pentose isomer can be sort of interconverted. And so here's an example of the isomerization of glucose, again, to allose. Now using 3 steps, but no protecting groups at all. These also proceed through the same aldose ketose isomerization kinds of pathways, though now using enzyme magic, we can access selectively or reasonably selectively the product of interest. I will say that because these are equilibrium controlled and also constrained by the temperature at which these enzymes are maximally active, the product distribution reflects the relative energies of the starting material and the product, right? These are equilibrium controlled processes and thus constrained in that manner. Okay, so my group was intrigued by a recent report of radical epimerization in the biosynthesis of neomycin B from neomycin C. So this is an enzyme that depends on the cofactor SAM. So first, single electron reduction by 4-iron 4-sulfur cluster forms 5' deoxyadenosine radical. This performs a hydrogen atom abstraction, selective at C5, to generate a sugar radical. This radical can then be quenched by pentant cysteine thiol, resulting in net stereoinversion selectively at the C5 position. So of course, in the context of an enzyme, a sort of exquisite architecture enables highly regioselective as well as diastereoselective hydrogen atom delivery, and also prevents the sort of internal quenching potentially of a very potent hydrogen atom abstractor with an equally potent hydrogen atom donor. Nonetheless, we sought to develop a strategy to do this kind of sequential 2-step epimerization outside of the context of an enzyme, of course, which would require addressing issues such as site selectivity, diastereoselectivity, incompatibility of reagents. Nonetheless, 2 really remarkable coworkers of mine, so postdoctoral fellow Yang Wang, who is joined by a second-year graduate student, Hayden Carter, took on this challenge, envisioning that if indeed 2 sort of sequential steps could be employed to affect this epimerization, that this would in principle enable kinetic control over the reaction outcome and therefore in principle high yields and selectivities higher than that might be accessed through equilibrium protocols. I should say that there is some extremely important precedence for selective, regioselective oxidation of carbohydrates, which I'll just highlight here. So work by Adrian Menard has shown that palladium catalyzed oxidation of alpha-methyl mannose gives extremely selective 2-electron oxidation to give C3 keto glucose. And with respect to epimerization, he's shown that completely free glucose also undergoes this C3 selective oxidation, and that in a 1-pot 2-step sequence, they can then reduce using sodium borohydride to get to mixtures of allose and glucose but in really excellent yield actually overall. They also showed that using LS selectride, they could actually improve to about 9:1 the ratio of allose to glucose that was obtained. More recently, Menard subsequently showed that C3 selective hydrogen atom abstraction could also be achieved with the same substrate and then trapped in this Giese reaction. This work was also developed using boron acid or boronic acid co-catalysis by Mark Taylor at Toronto. So basically, starting from these precedents, we identified conditions using a photocatalyst, quinoklidine, a thiol, and a base, whereby we could get essentially quantitative conversion of alpha-methyl glucose to alpha-methyl allose. There's a few control experiments, so no photocatalyst, quinoklidine, thiol, or light, no reaction. In the absence of base, reaction yield is quite poor. It's a little bit better using a commercial benzoate base rather than this sort of bespoke chlorinated benzoate base. The common iridium photocatalyst can be used instead of the CZ-IPN. The mass balance is a little bit worse in these cases, in the case of the sort of iridium system, and also it's about 1,000 times more expensive than the CZ-IPN, so we sort of stuck with that. Quinoklidine is uniquely effective in this reaction, as is the use of alkyl thiols as hydrogen atom donors. So among all of the different hydrogen atom sources that we assessed, really alkyl thiols were uniquely able to promote epimerization. Just a quick, I guess, NMR spectrum here. So here's just to show you sort of how kind of clean these reactions are. So here's a methyl glucose, and then the product methyl allose, and then here's a reaction crude. So it's basically, entirely methyl allose with maybe a little bit of starting material left over. So using this method, we identified that depending on the starting material, so glucose, galactose, mannose, for example, we can access 4 out of the 5 rare sugar epimers in a single step. So allose, talose, glucose, and altrose. A number of other sugars work under these epimerization conditions. I'll just show you a couple of my favorites. So here the reaction of L-ribinose gives approximately 1:1 mixture of pseudoenantiomers. So L beta-methyl ribose and D alpha-methyl ribose. So the beta-methyl ribose arises from C2 selective epimerization as highlighted in blue, but the D alpha-methyl ribose arises first from a C4 selective epimerization to give alpha-methyl xylose, which can undergo a ring flip, and then I guess over epimerization at C3, then to give the alpha-methyl ribose. And indeed, if we start with alpha-methyl ribose or xylose as a substrate, this is efficiently converted into the alpha-methyl ribose, consistent with a sort of scheme of this type. Glucosamine is also an effective substrate. This gives a sort of 1.5:1 or so mixture of the N-acetyl allosamine as well as a galactosamine product. Reaction works also on completely unprotected sugars, though in somewhat sort of diminished yields. So free glucose can be converted to free allose in about 38% yield, and a number of other free sugars also work with pretty good efficiency. If you've had the great pleasure of not working with carbohydrates in your life, let me, I guess, remind you or mention that when we draw a structure like this, we're not really drawing one molecule, we're drawing 5 molecules, right? So here is the purified NMR spectrum of 2-deoxyallose, and you can clearly see the alpha and the beta pyranose forms, as well as the alpha and the beta furanose forms, and then some portion of ring open form as well. I should also mention, as I sort of highlight this 2-deoxyallose substrate, that this is a substrate that would not be accessible, that would not sort of work under these equilibrium controlled enolization isomerizations because of the absence of a substituent in the C2 position. Disaccharides, trisaccharides also work. There's 14 stereogenic centers, right, in raffinose, and we isolate a single product with a singly epimerized stereogenic center. C-glucosides, so for example, empagliflozin is a diabetes drug, undergoes epimerization, as do these pyranonucleosides, though in pretty modest yields. On the basis of a few preliminary mechanistic findings, we propose this kind of biomimetic sequential hydrogen atom abstraction, hydrogen atom donation mechanism. So involving hydrogen atom abstraction by quinoklidinium radical cation generated from photocatalyst, gives a sugar radical in an HAA kind of a step, and then subsequent hydrogen atom donation by thiol to generate thiol generates the Alice product from the sugar radical. I'll show you a few of the experiments that led us to this conclusion. So first, we looked at Stern-Volmer fluorescence quenching studies under more or less optimized reaction conditions. Here we see effective fluorescence quenching by quinupridine, but not of an adamantane thiol. So consistent with this, I think now pretty well established method of generating quinupridinium radical cation to do hydrogen atom abstraction. And if we add thiol and quinupridine again, we really just see the same rate of fluorescence quenching attributed to quinupridine. So the presence of thiol doesn't seem to influence the fluorescence quenching step under these conditions. Importantly, no epimerization is observed in the absence of the thiol. So if we exclude the thiol and we increase the photocatalyst loading, what we recover is a small amount of this 3-keto, the 2-electron oxidized product. So we think that hydrogen atom abstraction works. However, we don't see any epimerization under these conditions. Similarly, if we run the reaction instead of with thiol with an electron deficient alkene, again, we can confirm that under these conditions, hydrogen atom abstraction occurs. So to generate this alkylated product, but we never see epimerization, again, unless we also add thiol into these reaction mixtures. Okay, so this set of experiments is consistent, again, with a quinupridinium radical ion mediated hydrogen atom abstraction to generate a sugar radical, which can be either over-oxidized or alkylated depending on the reaction conditions. But that is essentially what we propose as a functionally irreversible step under these conditions. So we then went back and did a similar series of fluorescence quenching experiments using now an aryl thiol, so a thiophenol derivative, this 4-bromo thiophenol. So under these conditions, we see no reaction. So again, quinupridine is effective at fluorescence quenching of the photocatalyst, but the thiophenol is not. However, in this case, when we add thiophenol and quinupridine together, we now see an increased rate of fluorescence quenching. And we attribute this to an internal acid-base reaction, right, where the quinupridine with its more acidic thiol deprotonates the thiol to generate a thiolate, and that the thiolate can then be quenched in an oxidative manner to generate the thiol by the excited state of the photocatalyst. And indeed, independently prepared sodium thiolate shows an extremely high rate of fluorescence quenching, again, consistent with the possibility that the thiolate, when more acidic thiols are used, is oxidized to the thiol, and that leads to no reaction. So this certainly opens the possibility that perhaps there is an internal sort of hydrogen atom abstraction process by the quinupridinium reacting with the thiol, even under conditions involving adamantane thiol, the sort of optimal thiol, that generates perhaps an active adamantane thiol radical. So to rule out this possibility or to explore this possibility, we looked at basically all of the conditions we could identify for the generation of thiol radicals. So either oxidative quenching of thiols or reductive quenching of disulfides or thermal conditions for the generation of thiol. And under none of these conditions did we see any epimerization reaction, suggesting that the hydrogen atom abstraction step by thiol is negligible, and there's essentially irreversible hydrogen atom donation by thiol, making this step essentially irreversible as well. So these conditions are these sort of, I guess, mechanistic experiments suggest the possibility of a kinetically controlled epimerization reaction, as do the sort of, I guess, anecdotally, the yields that we obtain are considerably higher than those that would be anticipated based on sort of established thermochemical measurements. Nonetheless, we sought to I guess, further establish whether sort of simple equilibrium mechanism could be operating. So for example, we looked at the reaction of L-fucose under our standard reaction conditions. This gives, under our best conditions, only a 70% yield of the C2 epimerized deoxytalose product, along with 12% of recovered starting material. So we sought to sort of run this reaction in reverse, right, as I sort of indicate with this dashed arrow. So we isolated the deoxytalose product, and we subjected it to the same reaction conditions. However, we see none of the starting fucose, and we see only the deoxytalose, albeit in sort of diminished mass balance. So at least for these conditions, this doesn't, or this substrate, this doesn't, seems like product formation cannot be rationalized by simple equilibrium model. One possibility, however, is that perhaps only the fucose CH bond can undergo hydrogen atom abstraction, and that the deoxytalose is not competent to enter the sort of reaction mechanism. So to examine that question, we looked again at methyl glucose. So our preliminary model compound, which is converted efficiently to methyl allose. We isolate the methyl allose and we subject this to deuterium incorporation conditions using deuterated adamantane thiol. When we run this reaction, we see 40% deuterium incorporation into the recovered product. We recover good mass balance in this case. And we see no glucose either proteated or deuterated. But the observation of deuterium incorporation suggests that, at least again, in this case, both diastereomers actually can react. So glucose and allose can undergo hydrogen atom abstraction, but that they're converging to a single, we propose, kinetic product. So with that, let me once again thank you for your attention, and thank you for the opportunity to share my group's work. Again, I'll thank Yang and Hayden who did this work, as well as the rest of my group. I apologize that this isn't an updated photo and some group members were excluded. But thanks again, and I'm happy to answer any questions.
So if anybody has any questions, feel free in the Zoom meeting. There's a Q&A box in the YouTube. There's a chat section. I can get, I'll get started. I mean, first of all, I just want to say this is really great work. I mean, I really enjoy seeing this. I mean, I think this is the type of chemistry that really, enables SAR, as you alluded to. The synthesis of every one of these sugars is long and very different, and just being able to interconvert is extremely valuable to both medicinal and process chem. Speaking from an industry perspective, so great talk. Thank you very much. I guess the first question that I'll ask is have you had any luck on say pentoses or nucleosides, anything along those lines?
Yeah. So just preliminarily, yes. So pentoses do work. Though I think that'll take a little bit more reaction optimization. So I didn't present it here, but yeah.
Oh, great. Looking forward to seeing it. And then I guess I'll ask one more. So I mean, you showed a lot of examples. Have you developed any set of rules that are predictive in terms of which if I throw a couple of different sugars at this, which alcohols might epimerize more likely?
Yeah. Let me maybe run back a few steps. So the short answer is no. Like I cannot give you like a predictive, what's a better one? A predictive model. What seems, okay, so very strongly, we prefer in glucose configured substrates, we always hit C3. And that's aligned with work that others have done. So Adrian Menard's work that predated us by, several years. So it's, I guess, so certainly substrate controlled, but it's consistent with the kind of selectivity that others have observed. We don't have a predictive model, but what I can tell you is that at least to our first sort of our initial attempts to sort of determine bond energies and sort of model what is, I guess, regio controlling, it doesn't seem to correlate simply with bond energy. So we really see no appreciable difference between the sort of C2, C3, C4 bond energies. And it seems more that the site selectivity correlates with the hydricity of that CH bond. So perhaps there's a sort of polar interaction between the highly electrophilic quinculdinium radical cation and the hydricity of the CH bond. So it does seem to be a sort of transition state effect, or like a pre-transition state effect, rather than a purely thermodynamic effect. But yeah, so sorry, I guess the short answer to the long answer is we can't sort of predict at this point.
It's really nice. I mean, I'm excited to try some of this in the lab. So we do have one question. Nick Champini says, love the talk. Have you seen any success with aminoglycosides? I think the oxidation deprotonation might be an issue for things like guanosamine. Thanks,
No, so the only nitrogen containing sugars we've looked at are these guys, right? So the glucosamines. So we haven't looked at like, just alkylamines or primary amines in this reaction. Although actually that's not true. So when we were looking at glucosamine, we look at the free amine and there was no reaction in that case. So perhaps as you're saying, there's some problem with either PCET or just electron transfer to the electron-rich amine. And also with an azido sugar, no reaction in that case as well. So also possibly interfering. That's a great point.
And you did briefly show. I'll just ask one last question. You did briefly show a conjugate addition from the radical. Is that something that you've explored further as well? Or?
Yeah, I think I just sort of in passing these alkylation. Yeah, this chemistry works also really well. So with electron deficient alkenes, a pretty broad scope again with this we have conditions essentially where we can get completely stereoinvertive reaction outcomes as well as very selective stereoretentive reaction outcomes in certain substrate classes. I will point the audience to work by again Adrian Menard, who really showed the first example of these kinds of sugar-Giza reactions, and then also Mark Taylor, who showed that cis diols could be activated towards these kinds of alkylations, towards stereoretentive, I guess, CH alkylation, sort of as a weird statement. So those two have also really contributed in this area. I think that there will be, in general, the substrate scope for these alkylations is simple electron deficient alkenes. And so I think that there's a good opportunity to develop either simple alkylations like methylations or formylations, so the kinds of alkyl motifs that are found in those rare sugars, or also things that are a little bit tougher like arylations and that sort of thing. So I think there's a lot of space that we're interested in that sense. But again, I'll point people to precedent work that I didn't highlight per se around these kinds of sugar alkylations.
Thanks. Looks like a few other questions actually just came in all at once. Tesha Buden asks, do you know what the fate of the reduced photocatalyst is in the absence of thiol?
No. Sorry, we didn't even dig into it. I'm sorry, Teshik. Forgive me.
Trevor Harris says, is there a similar manner to conjugate addition to, in a similar manner to conjugate addition to alkenes, will this work with alkynes?
I guess a tentative yes. So we have using, I guess, related chemistry to generate sugar radicals at other positions. We can get radical additions to alkynes. But I can't say that it would necessarily work in the specific regioselective outcome. But yeah, at other positions, we can get alkyne additions.
All right.
Sorry, that's, again, I'm sorry to tease something and then not have any data to show you.
Okay. We're all looking forward. I'm sure that will be there soon. Okay, one more question and we'll move on. Michael Perung asks, so is there no selectivity for C3 with GLICMAC, C4 also?
Yeah, so so again, I also don't show this data. So here's the glucosamine gives poor selectivity for allosamine and galactosamine. We actually can influence the I guess the regioselectivity by using sort of Mark Taylor's strategy, which is sort of Lewis acid coordination to sort of selectively activate one versus another. And so we can actually bias this either to enhance allosamine selectivity or to enhance galactosamine selectivity. I will say that galactosamine actually has to be, or very often has to be prepared, and it is usually prepared from, rather than sort of accessed directly, is usually prepared from glucosamine via an epimerization or stereo inversion protocol. So this would offer, if we could get these selectivities to be sort of quite high, this would offer, I think, a pretty good strategy, one-step strategy to get to good yields of galactosamine. I hope that answered the question. Sorry if I got confused.
I think, okay, we'll do one more because a bunch have come in and I promise this will be the last one. Monica Rivas asks, thanks so much for the awesome talk. Could you please comment on the origin of selectivity of the first HAT step? wouldn't we expect the anomeric position to have the weakest CH bond that produces the most stable radical to be reactive?
Yeah, isn't that, I mean, that again, that was my assumption too. I would thought that we would be able to hit C1 and C5 like no problem. And then it was C2, C3, C4 that were going to be a challenge. It turns out not to be the case. And again, that's also consistent with work that Mark Taylor and Adrian Menard and others have shown that, and also, you know, in calculations both done by us as well as Mark Taylor, it really, you know, the bond, the sort of pure BDEs of, again, as calculated of the C2, the C3 and the C4 positions are lower in energy than the C1. So it is, I think, a little counterintuitive, but also that we have to think about issues of radical polarity as well. And so again, I think that these, these kinds of conditions, these quincuclidine conditions, et cetera, are going to prefer the more hydritic CH bonds. And so that may be a complicating factor.
Great. Well, thanks a lot. So there's several questions in the Q&A, and you know, you can type answers to them. A lot of them are around designing predictive using work along a lot of mass Sigmund or Abbvie Doyle. But I think that would be a long discussion. So let's why don't we move on to Eric's talk and Scott.
All right. Well, thanks, Alison, for the awesome talk and all the engagement with everybody in the Q&A, and I'm sure you guys go on for quite some time, as Steve said, with the answering of the questions. So our next speaker is Eric Voight from Abbvie. So Eric received his bachelor's degree from the University of Minnesota Twin Cities and pursued graduate studies at the University of Wisconsin in Madison under Professor Burke. And after earning his PhD in 2004, Eric moved to industrial process chemistry, first Merck and then at Glaxo before his, where he is now at Abbvie. In 2012, he founded and runs now the current centralized organic synthesis group at Abbvie, which is at the interface between medicinal and process chemistry, an area that's full of exciting chemistry. I can assure you my own experience. So Eric has published over 50 papers and patents during his career, and through that work with process chemistry, has worked on over 30 clinical candidates. In addition, he's received numerous awards from various organizations, including a Abbvie President's Award for the discovery of ABBV 951, which I think is currently in clinical phase 3 trials, but I'll let him speak to that. And knowing how companies give out these awards, that's probably a very something very prestigious at Abbvie. In addition, Eric's been involved with the NSF CCHF for several years, and he's now been on the advisory board for the CCHF for the last 3 years. He's recently contributed to a Beyond Rule of 5 version of those top 200 posters that everybody sees and has posted around from the Nyarderson lab at Arizona, and I think it's going to be part of his discussion today. And on top of that, if that's not enough, he and his wife welcomed their 7th child in May. So I'm pretty sure most of this talk was prepared in the dark at 2 a.m. So without further ado, I'll let you, Eric, take over for this.
Thanks, Scott. Can you hear me?
Yes, we can.
All right. Thanks for the kind introduction. Alison, great talk. I met Alison at Wisconsin about 10 years ago. It's great to see how your program's developing at MIT. Really exciting work going on in your group. Thanks for sharing that. So this is a very different talk than I've given before. I shared at a CCHF virtual symposium a couple years ago. So no CH functionalization in this talk. I wanted to go a totally different direction. But it's really my pleasure to be able to represent a lot of teams of people who have worked on a lot of really tough molecules over the years in the antiviral space at Abbvie. So I won't be talking about any coronavirus research, although of course that's a very exciting area of research right now. But another really devastating virus is hepatitis C. And Abbvie's been working in this area for quite some time now. So I'll be sharing some work we've done. Typically in drug discovery, we try to stay in what's called the rule of 5. So we try to stay with smaller, less lipophilic molecules to hit the targets we're interested in. However, sometimes we're looking at targets that are more lipophilic or protein-protein interactions where we really need larger, more complex molecules to hit these drug targets. And this is an increasing area of focus across the industry, and that's what I'll be talking about today. So as I just said, well, these are the actual rules that Lipinski laid out in the late 90s for what we call the rule of 5. And really, this has been used to define drug-like space, as it's called, molecular weight less than 500, C log P, or the octanol water coefficient less than 5. Looking for less than 5 hydrogen bond donors, less than 10 hydrogen bond acceptors. And about 5 years later, a paper by Weber added a couple other properties that are also often included in the rule of 5, including total polar surface area less than 140 and non-rotatable bonds less than 10. So as I mentioned, back when these rules were published, the vast majority of orally available drugs were in this space. However, in recent years, there's been a lot of activity in what we call at Abbvie beyond rule of 5 space. So in the last couple of years, many reviews have been published on this topic, including one from my colleague David DeGuy and others at Abbvie, with some lessons learned at Abbvie. A mini perspective from Michael Schultz at Novartis followed a year later. We showed this interesting graph, just really very few beyond rule of 5 molecules up until the 1970s, most of which were natural products. And then in all the sort of recent 5-year time periods here, you see the number of larger orally available molecules really increasing very rapidly, while the number of approvals in rule of 5 compliant molecules has remained somewhat more constant. So review that is the most relevant for discussion today was published just this year by Kielberg in Sweden in Chemistry European Journal. I encourage you to look here for some more really interesting beyond rule of 5 synthesis stories. So another way to visualize this trend is looking at these density plots. So as you see, back when I was in grad school 20 years ago, the vast majority of oral drugs were in this molecular weight less than 500, C log P less than 5 space. However, in the decades following, the space has really migrated towards more and more outside of this rule of 5 space. And the reason for this really is not that we don't want to make molecules in this space. It's that we're really tackling many less druggable targets. So targets that are hard to hit. A lot of the targets that you can tackle that accept rule of 5 compliant chemical matter, a lot of those are taken. So it forces us to look at more complex molecules to bind targets of interest when they require it. So another way to look at this, so just in a specific 5-year time period, 2014 to 2018, there's a total of over 200 FDA approvals, and about half of those were oral. Out of those orally available small molecules, over 20% of them are actually beyond rule of 5. So we define beyond rule of 5 as failing more than one of those rules. And you see here is a vast array of therapeutic areas from many different companies. I've put in yellow boxes here the ones from Abbvie in both the HCV and oncology space. So we thought it would be interesting to collect all of these structures in one place. Many of you are possibly familiar with Professor Njardarsson's posters, his top pharmaceutical posters. So we use these as artwork in our lab here at Abbvie. Some of his top 200 pharmaceuticals. We decided to compile, we worked with Professor Njardarssson and compiled all the structures of every approved beyond rule 5 orally active pharmaceutical. And it came up with a total of 89 of these that break more than one rule. And we organized them by molecular weight, biggest being cyclosporin, which is a natural product that's been approved for quite some time. Very interestingly, shaded in blue here, all the antiviral agents. Actually, over a quarter of these molecules are in the antiviral space. So if anyone's interested in this, there's a lot of other information here. You can go to Professor Njardarsson's website and download this for free if you're interested in taking a closer look at these structures. So zooming in on 5 molecules in particular that are on that poster, these are all HCV molecules from Abbvie. So our first approved drug for HCV was Vicurapac, which is a mixture of ritonavir, paritaprevir, and umbidosvir, all in beyond rule of 5 space. More recently, Mavorut was approved, which is a mixture of glecaprevir, HCV protease inhibitor, and pibrentasvir, which is an NS5A inhibitor. As you can see, we're far beyond rule of 5 space here with molecular weight over 1100, a C log P of almost 10. So this really presented a formidable synthetic challenge for our discovery team and process chemistry teams to tackle these molecules. So for more information about this, this is just Maverick.com. Maverick's really a remarkable drug that's had a very positive impact on human health for the millions of people suffering from HCV. It's really the only 8-week cure for people across genotypes 1 to 6. It's currently the #1 prescribed chronic hepatitis C medicine. You can get more information on Maverick.com. So looking at the structures of glecaprevir and pibrentasvir, so my process chemistry colleagues were kind enough to let me present some of their work on making these things. It's really very challenging structures. I could go through all the details of these, but I just want to jump into some of the synthetic strategies in the interest of time. So the initial discovery and enabling synthesis strategy from process is shown here. A late-stage ring-closing metastasis reaction was implemented to close this ring. And the other portion of this molecule, this difluoromethylcyclopropane, was accessed in 10 steps from glycine ethyl ester. The macrocycle, as I mentioned, was obtained through ring-closing metastasis following an amide bond formation. Unfortunately, with a lot of optimization, this required a lot of catalyst and gave 10% cis isomer, which is very hard to reject. So despite this fact, this route was used to prepare over 41 kilograms of glecaprevir for clinical trials. But an improved route was really needed for manufacture of this drug substance. So this strategy, this was published on OPRD earlier this year. So several alternative strategies were investigated. One of them was a macro etherification. So retrosynthetically, this would take you back to this acid alcohol and this amino alcohol, which could hopefully be put together through an amide bond formation and macro etherification. This piece would come from the same starting materials as in the enabling strategy. Or I'm sorry, this right-hand fragment would come from the same starting materials as previously. So this allylic alcohol, to access this with very high selectivity, a cyclic carbonate shown here was assembled in 4 steps. Then this could be eliminated with very high EZ selectivity to give the allylic alcohol shown. The difluoromethylcyclopropane, greatly improved synthesis of this was identified from readily available starting materials, the key step being enzymatic resolution of this racemic Bach amino acid. After acyl sulfonamide formation, the key macrocyclization step was preceded by an amide bond formation. So amide bond formation, benzylic alcohol selective bromination, followed by macroetherification with tetrabutyl ammonium hydroxide. You have a very good yield of macrocycle, and then a final acyl sulfonamide formation gave, or final amide bond formation gave glecaprevir. So this route more than doubled the overall yield, and manuscript describing the synthesis has recently been accepted, led by Russell Sink, my colleague in process chemistry. So that's a very brief glecaprevir synthesis story in beyond rule of 5 space. So pibrentasvir, the other component of Maverick, is really in what I call far beyond rule of 5 chemical space. So it really sits out here on its own, together with cyclosporin perhaps. However, as I mentioned, cyclosporin is a natural product. So pibrentasvir is by far, to our knowledge, the largest orally available de novo designed drug that's currently exists. And there's been some excellent publications from my colleagues on the details of the medchem, the discovery of pibrentasvir, and this was highlighted also in this review that I mentioned before. So I encourage you to take a look at these papers to get more information about the discovery story. It's really some spectacular work. So pibrentasvir is, if I can advance the slide, sorry, oh, here we go. So if you look at pibrentasvir, as you see, is a C2 symmetric molecule. So this allows you to benefit from a 2-directional chain synthesis. So if you cleave these 2 amide bonds, it gets you back to this tripyrrolidine intermediate. This could be accessed by closing to the 2 benzimidazoles simultaneously in a 2-directional synthesis sense. This could be further disconnected via Buchwald-Hartwig CN bond-forming reaction in two directions, as well as a double SN2 reaction between this aniline and this dimesylate. Finally, the dimesylate can be seen as coming from this readily available acetophenone. So this original strategy that was implemented for the discovery synthesis was seen as suitable for large-scale synthesis and further optimized by our process chemistry colleagues. So to describe the synthesis in the forward sense, I mentioned two-directional chain synthesis. There's two really nice reviews in the mid-90s on this topic from Schreiber and Magnuson. And so, obviously a lot of efficiency to be gained when you can do two reactions simultaneously. So the acetophenone starting material could be brominated, and then these two molecules reacted together to form a 1,4 diketone. From there, a CBS reduction gave initially, so the first reduction did not take place in incredibly high selectivity. However, since there are two reactions taking place simultaneously, this can benefit from what's called Héroux statistical amplification. So basically, mesoisomer forming. So you get much higher selectivity of the RR over the SS at the expense of yield or ejection of the mesoisomer. So I will revisit this topic in greater detail in a few slides. So I'm not going to go over this in detail now, but this is a key stereochemistry forming step here in this synthesis. So preparation of an aniline was quite straightforward, and then union of this aniline with the dimesylate obtained from the RR isomer gave a complex triaryl pyrrolidine, which could not be isolated as a single isomer in good overall yield from the diol. So these reactions were optimized for over 100 kilogram commercial scale manufacture by J.C. Califano in process chemistry and his team. So from here, a bidirectional Buchwald-Hartwig amination was carried out. This was a very complex reaction that Shashank Shekar and our process chemistry group optimized. There's a really nice paper on this topic. It was a very interesting reaction. And from here, a double nitro reduction and cyclization to bis benzimidazole was carried out. Finally, a double DBOC and double amide bond formation with methoxycarbamate protected methoxythreonine proceeded in excellent overall yield to give pibrentosphere. So that is our current route to access both glecaprevir and pibrentosphere, which are our MAVRIT HCV drug. So where my group got involved was later in the game. While MAVRIT was doing incredibly well, you can imagine a molecule of this size and complexity is not especially soluble. It's actually very difficult to measure the solubility of pibrentosphere in anything. So because of that, we considered prodrug strategies. So soluble prodrug strategies are very popular as ways to enhance the solubility and pharmacokinetic properties, among other things, of drugs. So looking at pibrentosphere as a starting material presents many challenges. We really wanted to append one soluble prodrug functionality, not multiple. So because this is C2 symmetric, it presented many synthetic challenges. So the first is these O-methylthreonine side chains. These were prone to epimerization and beta elimination, so these were quite unstable under a lot of reaction conditions. These benzimidazoles, these are equivalent homotopic benzimidazoles that also present regiochemistry challenges with the up and the down nitrogens being quite similar to each other. There are two tertiary anilines in the molecule, which are reactive, as well as the C2 symmetry that I mentioned presents two homotopic ends, and differentiating those we knew would be a significant challenge. So we just submitted, and actually just today we have some requested revisions for an accepted manuscript that describes the medchem that went into identifying what I'm calling PIB prodrug A, B, and C. These are all alkylated pibrentosphere at this R position, this up position. So there's two esters, this one being a trimethyl lock, which is an interesting side chain, and this hydroxymethyl phosphate. So we did think initially about accessing prodrugs at the end caps. However, attempts to isolate NCAP prodrugs proved futile. So we abandoned those attempts early on. So in the original route that you'll see in this paper that was recently submitted, we would take excess pibrentosphere and react with a limited amount of a chloromethyl ester or some other alkylating agent to non-selectively alkylate one of the benzimidazoles. So in this case, we could isolate 19% of monoalkylated in about 1 or 2 to 1 ratio of up to down isomers. And then debenzylation gave PIB prodrug B. So this was fine for making gram quantities for initial testing. However, when we approached our development colleagues with this, they said really this would not be something we can consider as a development candidate unless we could get around a 50% overall yield from pibrentosphere due to the very high value of Mavorite. Of course, we can't throw away 80 or 90% of this for the sake of making a prodrug. So with that, we were tasked with the challenge of differentiating the homotopic ends of this molecule in desymmetrizing the homotopic benzimidazoles. So looking at complex C2 symmetric desymmetrization in the literature, I mentioned this Magnuson review in '95. So typically to avoid statistical mixtures, so 1 to 2 to 1 mixture of starting material mono to difunctionalized, this can be realized through either intramolecular functionalization or steric proximity effects. Without those available, so since this time, here's 3 more examples since the time of this review. One from Hoy in '96, where lithium acetylide gave statistical mixture of starting material mono to di, from which a 29% yield could be isolated of the desired mono functionalization. Actually, while I was in the Burke group, this reaction was worked on at Madison. A mono tebiolefination and in situ hydroboration gave a 40% yield of this halocondrin B intermediate. And 10 years later, Crochet published really elegant synthesis of the C2 symmetric diol, which could be desymmetrized again in 50% maximum yield to give this monoselenide, which was eliminated to give an alkene. So in our case, we were faced with the same problem, a potential statistical mixture, but actually this was even more complicated by the up-down nitrogen selectivity factor. So we not only had to monofunctionalize selectively, which hadn't really been precedented, but also had to deal with selectively either alkylating or protecting either the up or the down nitrogen selectively. So how would we do that? Not surprisingly, our initial attempts at Bach protection of pibrentosphere using catalytic DMAP proved quite ugly. Every possible isomer you can imagine was in there. So around 25% starting material, around 50% mono-Bach, which was a 3 to 1 down to up ratio. So slightly favoring the down Bach at room temperature. And then the other quarter mass balance being down dibach, up down, and up dibach. So everything imaginable. So after tedious chromatography, you could isolate the mono-Bach, and then serendipitously, there was a surprising solubility difference between these 2 isomers. So a single crystallization of this mixture gave a greater than 99 to 1 down Bach to up Bach in low yield, and the mother liquor was significantly enriched in the down Bach isomer. So this we hoped we could exploit this difference in selectively forming these. So how could we do that? I want to revisit the Haro principle of statistical amplification. So in the 70s, Haro published this first example of this. So using a 60% E phenethyl alcohol, or this secondary alcohol or secondary alcohol mixture, 80-20 mixture, 60% E mixture, you can statistically make carbonates from this. So I have the R isomer coded as purple here. And the 80-20 mixture reacts statistically with an 80-20 mixture of the same molecule to give these dicarbonates, either RR meso, which is RS or SR, they're equivalent, and then SS. So because the 80% reacts with 80-20 mixture, you get basically 0.8 times 0.8 is 64% of the RR. 0.8 times 0.2, you get 16% of the RS, and then the SR analogously gives meso, and 0.2 times 0.2 is 4%. So overall, your initial 4 to 1 ratio is enhanced to 16 to 1 with rejection of 32% of the meso. And then this was actually observed experimentally. Predicted EE was 88%. They observed 87% EE. They could cleave the carbonate, resubject this to upgrade all the way to 96% EE at the expense of meso. So this is a really powerful principle. So we often think of kinetic and thermodynamic effects as ways to get selectivity. Well, this is a statistical amplification that is not as commonly considered, and perhaps could be exploited in more contexts moving ahead. So there's a review on this principle that just came out a couple of years ago, a really nice review from Harned. You can look at it in tetrahedron. So how do we apply that in the context of Pibrentosphere? So in this case, again, I have, here I had purple and orange for major minor. Again, purple and orange for major minor. I mentioned at room temperature, Bach protection was 3:1. If we went to -35, it took a little longer, but we could get a 5:1 ratio of down to up. So 5:1 is 83:17. So if in this case we thought, well, why not just let it go to dibach? What would happen? So the 83% would, again, the second benzimidazole would functionalize with a 5:1 ratio to give, 0.83 times 0.83, that's 0.69. So 69% of the down-down. So the second one reacting it with in the up sense gives the up-down isomer. It's 0.14, but then of course the minor up-Bach also reacts in this sense. So analogously to the stereochemical statistical amplification, this is a regioisomeric heterocycle functionalization statistical amplification, giving in the end a 69:28:3 ratio. However, what's unusual about this is that instead of this intermediate compound being an undesirable mesoisomer, this also contains a down Bach. So both the 69% component and the 28% component has a down Bach if the up Bach can be cleaved selectively. So this is only useful if we can selectively cleave one of these two and the up Bach of this one, and leaving this 3% behind. So if we could do that, then we would have basically a 97:3 ratio of desired to undesired overall through the statistical amplification concept. So here's that 69:28:3 ratio here shown in blue, green, and purple. So blue, green, and purple, down, down, up, up. So now we have a kinetic situation where we found that butylamine and MTBE at room temperature, actually serendipitously, the up Bach was cleaved much faster than the down Bach. So K2 is faster than K1. So quickly the green goes away and generates this down mono Bach, which is this dark orange. And at the same time, the down-down dibach is slowly being consumed to also give the desired down mono Bach. All of the up dibach, the purple, gets rapidly consumed to give first up mono Bach and then Pibrentosphere in the light gray, which is of course undesired. I mentioned to you before that down mono Bach is not very soluble. So in MTBE, we can actually seed and crystallize selectively the down mono Bach, which protects it from further debach. We found that in acetonitrile, actually, the rate of down Bach cleavage is faster. So in the end, while we could, after 40 hours, filter and then reslurry in acetonitrile to give a 75% isolated yield of very clean down mono Bach, we found that after all of the up Bach was consumed, we could solve and switch to acetonitrile and get a more rapid completion of the conversion of this blue species to the orange species at the end to shorten reaction time. So each of these was just an overnight reaction instead of 40 hours. And then this also increased our yield to 85%. And then we could resubject mother liquors if desired to get another 10%. So we could get yields in the mid-90s of down mono Bach from Pibrentosphere. So you can imagine the NMRs of these things are kind of look like fluffy pillows. So we got a crystal structure of the down mono Bach Pibrentosphere. As you can see, the Bach is para to the fluorine. So that's exactly what we thought by through NOE studies. So it's confirmed with the X-ray of the monohydrate of this material. So from that, as I mentioned, we still had a very difficult challenge in how do we get a selective up alkylation of the remaining benzimidazole. So from this, my colleague John Hartung in process chemistry thought that forming a formaldehyde adduct may give a species that could equilibrate and preferentially react with some process to give the desired up alkylation. So John found that crystallization of this from ethyl acetate MTBE hexane gave a solid that he then looked at many different leaving groups in acylation using this benzyloxy phenylacetic acid acylation agent. So with increasing leaving group susceptibility, the selectivity increased steadily from 1.7, 1.8 to 1, all the way up to 20 to 1. What's very interesting is that crystallization of this adduct was required. So you could make this adduct in solution, but if you did that, then even with the acid chloride, you were back to very poor selectivity. So this was a very interesting, again, a crystallization-induced selectivity in that the crystallization of this compound gave just this one isomer, and then when you kinetically acylated it at low temperature with the reactive acylating agent, you get very good selectivity. So we hope to apply this with the prodrug relevant acylating agents. So we found that under different conditions, we could get a very high yield of crystalline hydroxymethyl. And from this, we could acylate under similar conditions in very good yield and deprotect. Otherwise, we could deprotonate that hydroxymethyl at cryogenic conditions and also get this PIB prodrug A after deprotection. For the trimethyl lock, PIB prodrug B, we found that the rapid deprotonation acid chloride quench was preferable, giving a 29 to 1 regioisomer ratio. We found with this, again, if we deprotonated for more than 2 to 3 minutes, the selectivity went down from 30 to 1 down to 1 to 3 to 1. So because of this, we actually used flow chemistry. Drew Bogdan, our high throughput chemistry group, did this on 100-gram scale and flow so we could accommodate these very short reaction times. Finally, the hydroxymethyl could undergo phosphate formation with this phosphoramidite reagent to give a good yield of PIB prodrug C. So overall, our yields for each of these were improved from very poor to around that 50% value that we were targeting. So in conclusion, I hope you've seen that beyond rule of 5, molecules provide a lot of exciting opportunities for innovation and synthesis. And as Scott mentioned, I work at a group at the interface between discovery and process chemistry. There's a lot of exciting molecules that we really see as opportunities for exciting new chemistry and impacting the pipeline at Abbvie. So I hope I've also shown you that organic synthesis is really critical for driving the discovery of the next wave of medicines. There's an excellent review from Merck on this topic in Science published last year that I'd encourage you to take a look at. With that, I'd like to thank my group. Here's a picture of my group from last summer before social distancing. Everyone's names are here. I'd like to thank Professor Njardarson, University of Arizona, collaborator on the Beyond Rule of 5 poster, as well as colleagues I've mentioned from other areas of the company, and certainly the large process chemistry teams that developed the Maverit synthetic routes that were kind enough to let me present their work. Finally, thank you for your attention, and be glad to take any questions.
Wow, thank you, Eric. That was really something. Yeah, definitely not flat land there for sure. Yeah, that was some. I just don't even know where to begin. There's so much math. That's a great job. While we wait for a couple of questions to pour in, I just really impressed with that the deprotection of the deblock with the N-butylamine and the crystallization in MTB. I mean, those are two things that you definitely don't do in one experiment, and being able to find that and just in a screening sense and then utilize that on that kind of scale is just some really impressive work. I mean, you don't just start with hey, let's mix this up and hope it crystallizes. That's really summarizing a ton of work right there. It's really amazing stuff.
Yeah, thanks, Scott. Yeah, the deblock worked better. We tried initially with just the deprotection conditions, but of course, typical acidic deblock condition or under the we tried acidic deblock, but of course under acidic conditions, things are protonated, and you couldn't get the solubility difference. So using the butylamine for the deblock to just transfer the Bach from the imidazole to the alkylamine ended up being much better for these solubility differences.
Mm-hmm. All right. Well, we've got a question here from Nick. It says, great stuff with the final prodrug. Was there any issue with purging palladium from the hydrogenation in the last step? That can be an issue.
Yeah, that was tough. We definitely had to get rid of that. There's some sensitivity of the final molecule, and we were still in the search for a solid form of this to get a solid crystallization, but actually up to the point where we took the project, we were still isolating the final product by chromatography. So that was very effective at removing metals. But that's certainly something that we would have had to address in more detail once a solid form was identified. But we didn't. My group didn't take things to that stage. So, but good question.
Yeah, here's one an interesting question from Jeff Obe. To what degree do you think these efforts have benefited from lessons learned in natural product chemistry? You mentioned a number of those references in the middle of the talk about learnings from natural product synthesis. Is there anything you apply that you learned from there directly impacting the work you've done here?
Yeah, I think it's really remarkable how much natural product synthesis literature we come across when we're looking for functional group compatibility in these very complex settings. Looking at the Brent-sphere as a starting material, there's just a lot of functional groups there that you can see and find in natural products. So a lot of the literature precedent for things that we try will come from natural product efforts, where precedent for functional group compatibility of reaction conditions is well precedent and fleshed out. So definitely, it's very important that work is published, and we certainly benefit from that.
See, I have a question about this mesylate that you made and the way to make the pyrrolidine. Seen that a few times, but you had a number of electrophiles in that molecule at the time when you tried to displace those mesylates. You've got reactive SNAR substrates there. You've got 2 chlorides and 2 fluorides that are in general terms pretty hot electrophiles for SNAR, but you went right to the pretty high yield of the mesylate displacement.
Yeah, this was I didn't do this work justice. I mean, every single one of these steps was really some incredible work done by people in process chemistry. But the lutidine base was really critical here. There were certainly many byproducts that were potentially formed here and were actually observed, but a high yield of the desired SN2 could be favored under the right reaction conditions. But certainly, if you had the wrong solvent to the wrong base, you could see any number of major products like the SNAR products that you recognize there. But yeah, you have these are all very reactive electrophiles for SNAR. So yeah, that's a great point. But yeah, under the methane sulfonic anhydride lutidine conditions, the double SN2 could be strongly favored.
Nice. Yeah, seeing all the chemistry here that you've been going through and knowing how that works in an industrial setting, it's definitely a huge story. And to tell the whole story in this short of a time, you definitely have to skip over a lot of the amazing work done by the folks in the lab, and true kudos to them, and to everybody on the team. All right, well, I'm not seeing any additional questions at this time. So I think we're just going to wrap that up. Steve, if you have any final comments, I'd like to thank Eric and Allison for just amazing jobs today. Thanks to Rio for running behind the scenes, and all the folks involved in the CCHF and the virtual symposium series here from the DOC. Appreciate everybody's attention and the wonderful talks that we had today. Steve, anything to add before we go?
Nothing on my end. Thank you very much to everybody. This has been a really great series, and we're looking forward to the ACS related EWOC and EWOC virtual events, and we'll see you back for this series in a couple months.
All right, now everybody does the end of the Zoom wave. All right.
Thanks, everybody.
Thank you, everyone. Have a wonderful day.